wanted to make sure that we hit. Namely, that we can work with differentiable, piecewise functions and still talk about the derivative. Now, what does it mean to be differentiable at a point? Okay, so for that, let's go back over to and just remind ourselves what the limit definition was. Well, let me just copy and paste this. Okay, so we've defined f prime of a to be this thing, okay, right, the different limit of the difference quotient. And we say that f is differentiable okay, provided that that limit actually exists, right? So we're setting up a limit, and that thing may or may not exist, like any limit. And if it does, why am I wearing these still? This is like the second time I've done that, isn't it? I'm like, okay. So if that limit exists, then great, the function is differentiable at that point, and the derivative is the value of that limit. And if that limit doesn't exist for whatever reason, then, well, sorry, it's not differentiable. And we'll look at some examples of when this happens. So before we actually do the one that's on the screen, let me start with, and let me switch the input over to the Elgato for if we have Thomas or anybody else online. Not now. Don't want hello Siri. Okay. So yeah, those of you who are online, I for some reason can't see the chat right now. Oh no, I can. Okay. So all right, so that limit could exist, it could not exist. So let's take a sort of classic example of where this is an issue. Absolute value of x. So what's the graph of that look like? Yeah, just a v, right? So, oops. All right, so it's that. And it's defined formally as a piecewise function if the thing you plug in is positive or 0, you just don't change it. And if the thing you plug in is negative, you throw an extra minus in front of it, and 2 negatives makes it positive, so that flips it back positive, okay? So that piecewise definition is actually what we'll use to sort of formally talk about the absolute value, okay? Now, the issue, we can kind of see what the issue is graphically. So what's the slope of the tangent line on the left-hand part of this? Yeah, -1. What about on the right-hand part? Okay, so we got a problem potentially where they meet, okay? So everything's cool except possibly at the point at the origin where on one side the slope is at one number and on the other side the slope is a different number, okay? And okay, so what value of a are we interested in at for this particular function? A equals 0, right? So I want to consider the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. Okay, so that's the difference quotient specific to the point 0, which is what we were interested in. Good? Okay, so now the issue that we have, though, is that h, okay, this tiny quantity, nobody said it had to be a positive number, okay? So we have a limit here where we're approaching h equals 0 from two sides. But the function is defined differently on one side versus the other. So what we need to do is break this up and do the left-hand limit and the right-hand limit separately. Okay, does that make sense? All right, so first, let's do the left-hand limit. Okay, so here, if h is approaching 0 from the left, thinking in our minds, right, small negative numbers. So if I do f of 0 plus h, what is the quantity 0 plus h? Is it positive or negative? If h is approaching 0 from the left. Negative, okay? And what is the function defined to be if the input value is negative? What is the definition of absolute value? What do? You just throw another minus sign in front. Okay, so for this particular value of h, the function is negative the input. Okay, so it simplifies to this. Okay, and what's f of 0? Just 0, okay. Okay, so that step's the hardest one of them. But let's make sure that we're cool with why I put the minus in this case. Bueller. You guys are supposed to say he's not here today. Haven't you guys seen Ferris Bueller's Day Off? Yeah. Once. All right, well. Okay, so now we just carry through, and in this case, what do we get? Negative h over h. And so we're taking the limit of -1, right, because the h's cancel, and that's -1. Okay, now that makes sense, right, because what did we say that the derivative, the slopes of the tangent lines were on this graph on the left-hand part? -1, right? Seems reasonable. Okay, and when we do the right-hand side, what do you expect that we're going to get? We should get 1. Okay, because that's what we thought from the graph, but let's just go through and work it out. So here, we need to do the same thing, but we're approaching, h is approaching 0 from the right this time. Okay, and if h is approaching 0 from the right, 0 plus h is what kind of quantity, positive or negative? Positive, okay, so that means who's in charge of the function? Like which, if I scroll back up to the piecewise definition, we're on the top part this time. Okay, so the input value is exactly the output value. And so we just get 0 plus h minus 0 all over h. Okay, are we cool with that part, right? Because again, that's the hard step. Okay, all right, and then the rest of it happens similar to before. Okay, and so we get 1. Okay, so does that make sense? All right, so left-hand limit was one answer, right-hand limit was another, and so what is the conclusion? Yeah, the limit So in this case, because the limit didn't exist, the difference quotient limit, the function f is not differentiable at 0. Okay, Now, what this also shows us is differentiability is like continuity in the sense that you can be differentiable at one point, but not differentiable someplace else, local property. This particular function, the absolute value, differentiable at 0, the one problem point. Right? Now, other functions we could cook up, just imagine drawing a couple of squiggles, like a W shape or something, right? Could fail to be differentiable at multiple points. And you could kind of keep that game up so you can, make a function fail to be differentiable as many times as you desire. But, it can be okay at one point and not okay at others. There is actually an example of a function that's differentiable nowhere. So it's sort of like infinitely jaggedy, if you will. It's a really weird function, though. And if Dr. Brown walked by, he would say, that's not a function. That's something that you mathematicians invent to be evil. Yeah. Although, I just realized the other day, we will never have the joy of Dr. Brown walking by during class to make fun of us or for us to give him crap, because he teaches at this exact same time in a different building. So, I know, the struggle is real. Okay, so if we were to come back to the other example, the one that's on the screen, let me switch back to that. Well, I'll just write it down. Why don't you guys work this one out? Okay, so first off, where do you think the problem point is for this one? Yeah, 0 is the problem point because that's where the two different definitions meet. Okay, so kind of do like what we did a minute ago. Okay, to determine, tell me, is G differentiable at 0? And if so, what is G prime of 0? And if not, well, then you would have told me that it's not differentiable. Okay, so let's take a few minutes and work that out. I need to get like Jeopardy music or something that I can put on the stream and while you guys are working things out. Get sued for, yeah, get a takedown strike or something. How you doing, champ? Good. Uh-oh. You need to charge. There's power in the desk. Yeah. Or there's just one right over there, too, but... You don't have two chargers? No, this charger is like weird. No, I know, but why not buy a second one? Yeah, leave one at your desk and keep one on your back. What do you think I do? Yeah. Are you kidding? It would be very difficult to get any work done without a computer in my life. And yet there's a time I remember, like, where I had an allowance of the number of hours per week I could be on the internet, and it was a single digit because we had dial-up internet back in the day. And huh? Yeah, the struggle was real. So we got the start at least. So what's the first step on both limits? So I've written down the two difference quotient limits that we need to do. One from the left, one from the right. What's the first step of the first one? What do I need to write? So limit h goes to 0 from the right, or left, sorry. Okay, if h is approaching 0 from the left, which line of the function is in charge? Top line or bottom line? Bottom line in this case, okay? So what is g of 0 plus h? Well, what is g of x for negative values? Okay, let me rephrase. What is g of x if x is a negative value? 2x plus 6, okay? So if I want g of 0 plus h, and 0 plus h is a negative value, what do? Everywhere I see an x, I'm going to replace it with 0 plus h. Okay, what is g of 0? 6. Okay, do we agree that g of 0 is 6? Okay. And do we agree that I've correctly plugged in to the correct thing, no less, right? Okay, what about the first step on the other one if we're approaching from the right? What stays the same? What g of 0 is, right? That doesn't change. But what's different this time, which part of the function do I plug into? The top one. Okay, so if I plug 0 plus h into the top one, what do I get? 0 plus h squared plus 2 times 0 plus h. Then I have to subtract off the 6. Okay, so are we Gucci with that setup? No. So the first two terms are g of 0 plus h, right? So that's this and this. The minus 6 is there because the difference quotient, I have to subtract g of 0. Okay. But no, g of 0 can only be one value, right? Which one is it? So look back at the definition of the function, right? So g of 0 can only be one number, right? If it were two different numbers, what would be the problem? Well, then we wouldn't even have a function at all, right? Because what's required to be a function? For any input, how many outputs can you have? At most one, okay? You could have 0 if it weren't defined, but at most one. You can't have 2, okay, and still be a function. Okay, the other reason that we know we're cool here and that it doesn't have that problem is because notice that the top line is only valid for x bigger than 0, not greater than or equal to 0, right? Okay, and so that's sort of how we save ourselves. Okay, does that make sense? Okay, good. All right, so are we cool with the two setups? Okay, so what does the first one come out to be when all's said and done? 2. What about the bottom one? Also 2. Okay. And actually, you know what, I'll write it this way. The dot dot dots are, you guys did some work, yes. Yes, yes, you can. And in fact, that's what we're going to do next. The benefit of at least right here doing it this way is that 0 is the point that we were interested in, right? And the point 0 front and center into our mind. But yes, we will do that. Okay. Okay, so does that kind of make sense? Okay, so in this case, what's g prime of 0? 2, the common value of the limit. Okay. Okay, well, yeah, let's work that one out because it's going to take a little bit more work. So what do we get? H squared plus 2h. Oh, interesting. Minus 6. Okay. Well, this limit doesn't exist. Well, no, you're right. We don't get 2. We get does not exist here. Yeah, okay. Now, how do I know that this limit does not exist? Yeah, I can't get rid of this h that's in the bottom, right? Now, I could do this and split the fraction up. And it's this term that's the problem. What's wrong? Well, what's g of 0? Right? G of 0 has to be defined by the first one. Right? Okay, now, here's another reason why this is happening. So what does the graph of this function look like? Well, what does the graph of each piece look like? The top piece is a parabola, okay, and the bottom piece is a straight line, but what's its y-intercept? 6, not 0. Okay. The top function, however, what is it approaching as x gets close to 0? So we've got a jump discontinuity here, okay? And in fact, why don't we graph these? So let me pop open to Mathematica here. And let's see, we want, where is Mathematica? Here. Okay, so if I, for example, plot the two functions, so x squared plus 2x, and what was the other one, 2x plus 6, and I'm going to graph these from, say, -2 to 2, because that puts 0 right in the middle. Okay, the problem is, so I've graphed both functions over the entire region, but only one of them is in charge. So basically, up until 0, it's the orange curve, and from 0 on, it's the blue one. Okay, so is this function even continuous at x equals 0? No, it isn't. And one of the things that we'll talk about later is that in order to be differentiable, you must first be continuous. Okay, but it doesn't necessarily work the other way. So absolute value of x, the example we started with, was that continuous at 0? But it wasn't differentiable there. Okay, so the logic goes one direction but not another. It's kind of like a square is a type of rectangle, but not all rectangles are squares, right? Same sort of idea. Okay, so does that kind of make sense? All right, now what about if we had slid the bottom function down? So what about if we had redefined it to be 2x instead of 2x plus 6? Maybe it would have worked out differently. Okay, and in fact it would have, because if we had done so, we would not have this -6 there, and that was the whole problem. Yes, but we would lose it in both places, because then we would have this plus 6 would become a plus 0, and this minus 6 would always be 0, and so it wouldn't matter, right? Okay, so does that make sense? Yeah? Okay, so, yeah, good. Well, that was fun, I hope. All right, so we've done a lot with the difference quotients. Let me open up, and this is actually what Sonny was just kind of saying. So let me switch the input back over to preview, but this time I want the window capture to be this one. Okay, so let's see, we want this here. Okay, so we won't use this website thing, but what have we done, right? When we defined the definition of the derivative as a limit, and we said the derivative at this point is this number, okay, whatever the value of the limit is. We did that for just sort of a generic value of a, and we were thinking of a as being whatever point we were interested in. But could we think of that as actually being a variable? Okay. So let me take an example. Okay. Let's take f of, oops. Dang it, that is not what I meant to do. This is what I meant to do. Let's take the example f of x is x squared. Okay? Perfectly fine. Pick a couple different values of a. Okay? For example, a equals 0. Well, first off, if I graph this, what do I get? Something like this. Okay. So at x equals 0, what's the slope of the tangent line at that point? That one's easy to see from the graph. It'd be 0, right? It's horizontal. Okay. So at that point, the slope is one number. And if I pick a different point, I'm going to get some other slope. So for example, if I pick over here, right, that has some slope. Maybe it's 2, roughly. I don't know. Okay, actually, it is 2. But let me actually show you guys something cool for parabolas. And this only works for parabolas, by the way. Okay, so I'm going to draw a nice big, actually, I'll do it in blue. Nice big parabola. Okay, let's pick a point on it. How about x equals 1? Okay, so the point there is 1, 1. Good? And I'm still doing x squared here. Okay, so what I'm going to do is I'm going to connect from my point to the axis, okay, a straight line that's perpendicular to the y-axis. Okay, and then I'm going to look at that quantity there, or that length there, okay, which is called the abscissa. Okay, it's a part of the diameter that's cut off by me dropping that perpendicular. Okay, what is the length of, and I'll highlight it in orange here, what is the length of that orange piece? 1, okay, for the particular point I chose. Okay, all right, now, this is a parabola. It has a vertex. Take that 1 unit distance and go that same distance to the other side of the vertex. Okay, so in this case, my abscissa was 1, so I'm going to go 1 more unit past the vertex along my axis. That gets me a second point, right? Take this point, take that point, and connect them with a straight line. What do you get? The tangent. Voila. Okay, and this works at any point, but only for parabolas. Sorry. Yeah, that's the downside. Okay, so who came up with this? No, very much not. This is Apollonius's construction of a tangent. So it's about 200 BC, BCE. Right. So this you can find this in Book 1 of the Conics. Yeah. So anyway, so yeah, that's how you do it. Now, we could do this construction for a whole lot of other points along the parabola, right? Or for that matter, yeah. So if we did that, okay, for each point that I pick, it has a slope associated with it. So why don't we make a new function based on the values of those slopes? Okay, and so what we'll do is we're going to define the derivative as a function, and we'll define it this way. Now, doesn't that look just like what we've done? What's the one thing I changed? I mean, in a sense, I almost didn't change anything, but I did. Mr. Amore, what did I change? Yeah, it's x instead of a, right? So before we were thinking of a as being a specific known pre-chosen value, but could I let it sort of be an unknown thing, right? Or let it be a variable? Sure, why not? Okay, and so now what we'll do is we'll define the derivative not as doing this point by point, but sort of thinking about doing it point by point for all the points simultaneously, and then that generates a function as the answer. Okay, does that make sense? All right, so let's do this for x squared. That's maybe the best example. So, for example, based on our construction here, what is f prime of 1? What was the slope we got of the tangent line at that point? 2, okay? And what was f prime of 0? 0. And what would have been f prime of -1 had we done that? Okay, and how did you know it was -2? Because symmetry, right? Okay, and we could have done that for a whole bunch of other points. Okay, well, let's do the limit definition, and then we should get a function that if we plug in 1, 0, or -1, we get out the values 2, 0, -2. Does that kind of make sense? Okay, so now we just have to do some limit crunching. All right, and well, I should have enough room here. All right, what is the function in this case? X squared is what I picked, right? So what is f of x plus h? What do I have to do? X plus h squared, right? So I'm going to substitute that into the function, subtract off f of x. So that's our setup. Okay, are we Gucci with that? Oui ou non? Okay. All right, so that's the setup, but now what do we got to do? What's the first thing we got to deal with? We go into the kitchen, we get our heavy duty foil, right? Oh, come on, I don't get a chuckle out of that one. You guys are, yeah. And I haven't even had coffee yet this morning. All right, so what do we get when we FOIL it? X squared plus 2xh plus h squared minus x squared all over h. Yes? Okay, and of course, remember, be careful when you FOIL, and be careful with minus signs if there are any, because if anything, those are the two places you're going to make the mistakes. Okay, so what happens to, from this point? What can we do? Right, we can cancel out a whole bunch of stuff. Oh, and I need to go back to the Elgato for one line. So some stuff cancels. In this case, just one term, the x squareds do. That's, oops. Happens. Okay. All right, so we're cool that the x squareds cancel, but nobody else, at least not immediately. Okay, now what can I do? In the top, okay, so if I factor an h out of the numerator, what's left in the numerator? 2x plus h, right? Okay, by factoring that h out, what does it make really obvious that I can do? Cancel the h in the bottom with it, so this dude and this dude are gone. And then now I'm just taking the limit of 2x plus h. Okay, now at this point we've got sort of a cognitive problem. As h approaches 0, what is 2x doing? Does 2x have anything whatsoever to do with h? No, x is a completely different variable. So as far as we're concerned, 2x is a constant when we're doing this limit. Okay, what about h? What, as h approaches 0, well, what is h approaching? How about 0? Okay, so this whole thing goes to 2x. Okay, does that kind of make sense? Right, x and h don't have anything to do with each other. Two completely different variables. So as far as h is concerned, x is a constant. Okay, so we got here this function. So we think if f of x is x squared, then f prime of x is 2x. All right, now let's look back up at our parabola. Does that jive with what we got here just by doing this geometry business? If I plug 0, 1, and negative 1 into the function 2x, do I get the correct slopes? I do. Okay, ones that we got with our geometric construction. Okay, that's good. That means we're doing something right. Okay, so does that kind of make sense? Yeah? Now, how many of you guys are sitting there thinking, Dr. McKinney, going from x squared to 2x should have taken 5 nanoseconds? Okay, because you know the tricks. Okay, you have illegal information. Yeah, well, okay. So there are some shortcuts for doing this, and we'll talk about those. Okay, and in fact we'll start sort of talking about that now. So yes, there are shortcuts for doing this. Be careful what you wish for, though, because you just might get it. Because what happens when you do have the shortcuts? The problems get real nasty, right? Okay, so the shortcuts, and there's, like I said, a whole bunch of them. If the problem is to do it with the definition, that means doing it this limit stuff, okay? For everything else, the shortcuts are permitted. Okay, so yeah, so when definition of the derivative, you're going to have to do limit stuff. Okay, sorry. Well, back in my day, we didn't have the shortcuts. We only had the limit. No, not really. Okay. Yeah. All right. So let's sort of figure out. Well, how did x squared to 2x? So what's going on there? Like, what do you think is happening, Mr. Burns? Since you know the trick, what's the trick? Yeah, so x squared becomes 2x because I'm going to take the exponent and put it out front and take 1 away from the exponent. So x squared becomes 2x to the first. Seem reasonable? All right, well, let's see if this pattern holds. So let's do it for x cubed. What would be your guess for what the derivative should be according to the Burns rule? 3x squared? Does that seem reasonable? Exponent comes out front, take 1 away from the exponent. Seem Gucci? All right, but let's prove it. Not just trust Mr. Burns, because who knows? He could be lying to us. I mean, look at him sitting there in that purple sweatshirt looking all shifty-eyed. Right? Okay, so what do we got to do? We've got to do, limit h goes to 0 of f of x plus h minus f of x all over h. Okay, what is x? What is the function? X cubed. So what do I have to do to my x plus h here? Oops. Yeah, I got to cube it. Okay. Now, for the sake of time, let me just amaze you with my algebra skills of amazement. Okay, so I just cubed it out. Does that look familiar? How did I do that so quickly, other than I'm the dude with the PhD at the front of the room? Pascal's triangle? Do you guys remember that from high school? No? All right, I'll show you that some other time. Just trust me on this part, I'm a doctor, okay? Okay, but in particular, what happens similar to last time? Okay, yeah, I foiled it. It was a little messier, but what happens here, what's the next step, is to start to cancel stuff step, right? What cancels right away? Yeah, the x cubes. And so, like before, what is left in the numerator? A bunch of terms that all have at least one factor of h. Okay, so I can factor that out, leaving this. Okay, good. So the hardest part on this one is the foiling, and like I said, just trust me for sake of time. Okay, now for the limit. Let's actually work it from the back to the front. So what's the limit as h goes to 0 of h squared? That one's 0, okay. What about 3xh? Also 0. You say that with such enthusiasm. What's this one? Thank you. Yeah? Okay. Hey, we're on to something. All right, so if we did this for x to the 4th, what do you think would happen? 4x cubed. Okay, it'd be kind of messy. Fortunately, I know a lot of really cool ways to foil things out. Okay, because I have wizardry math powers. Yes, this works. Okay, in fact, it even works for non-integers. All right, so one of the early examples we did was we had a function, this. What did we get when we did the limit derivative stuff? Okay, we did that, I think we did it last time. Maybe it was last week, I don't remember. No? Well, okay, let's just go through it. When I start to write it down, I think you guys will remember. Okay, so does that ring a bell? Okay, what was the trick that we did here? By the conjugate, exactly. So I'm going to multiply by this guy, and then as thou doest unto thy numerator, thou shalt doest unto thy denominator. Okay, so do we remember using the conjugate trick before? Okay, it's the thing that you would have never thought of on your own unless I locked you in a room and said you can't come out until you figure it out. Maybe eventually you would have figured it out, but yeah. But now that you've seen it, you can never forget it. Okay, so what's so brilliant is if I multiply everything out on top, what happens? I get x plus h minus x okay, why did I only get two terms on top? Right, what's the whole brilliance of the conjugate? When you FOIL, what happens to, to the O and the I, the outer and the inner pair? Yeah, they're exactly the same, but with opposite signs, so they cancel each other out, and all that's left is the first and the last, but because it's square root times square root in both cases, the square roots go away, and I just have x plus h for the first term and minus x for the second one. That's brilliant, because then what happens? The x's cancel, and then the next step, the h's will cancel. That's plus. And so we get limit as h goes to 0 of 1 over x plus h, square root plus square root of x. Okay, now, here we have to be a little bit careful. Is it a problem if I just plug in h equals 0 here? Do I get a division by 0? No. Okay, so I can do that. And if I plug h equals 0 in, then what do I get? 1 over root x plus another root x is 1 over 2 root x. Okay. So, if we think our rule is correct, the power rule, that's what we'll come to call this, says take the exponent, shove it out front as a coefficient. Take 1 away from the exponent. And so the Burns rule will be 1/2 x to the minus a half. Is that what we get when we did it the limit definition way? Are they the same thing? Yes. Okay. So, shortcuts ahoy. Yeah. All right, Gucci? All right, I'll see you guys on Friday.